Big old nerds, all of you, bunch of big old nerds. Well, anyway, what? He's already talking some crap? Afternoon class, let's get to it. Today we're going to start lesson 2. We won't finish lesson 2, but we're going to put as big a dent as possible into it. Okay. So there's a lot of words here, and these words are basically just telling you why we care about trigonometry. It's talking about a couple places in life where it might be useful to you. Look, it's very useful to you, okay? We are going to start our journey by talking about angles and some of their properties. So just like we did with lesson 3.1, we got verbal vocabulary and what that looks like as visual vocabulary. First of all, this one requires you to know a vocabulary word from geometry, and that is what the vertex of an angle is. The vertex of an angle is the place where two rays intersect. So this would be an angle, right? This would be known as the vertex of that angle. Okay. So what is standard position? An angle whose vertex is at the origin 0, 0 of a coordinate system. This is the xy plane. And one of the rays is on the positive x-axis. This is known as an angle in standard position. So one more time, vertex at the origin, and one of the two rays is on the positive x-axis. That ray that's on the positive x-axis is known as the initial side. Any angle in standard position, the ray or side of the angle that is on the positive x-axis. And it should say positive. So this is the initial side. The other ray, this thing, where the angle comes to an end, is known as the terminal side. Terminal meaning ending. The terminal side. So if terminal means ending, then coterminal means ending together. Coterminal angles are two angles in standard position that have the same terminal side. I'm going to draw something to show you what that looks like. You don't need to have this drawing. So let's say I've got my XY plane here. I'm going to throw an angle on here in standard position. There it is. I'm showing you this is that angle. I'm actually showing you where it started and where it ended. But I'm hoping we can all agree that an angle that starts here and ends here could also have been done like this. Do you see how both my red and my blue angle begin and end at the exact same spot as each other? These two angles would be known as coterminal angles because they begin in the same spot, they end in the same spot, but they do not have the same measurement. That's what coterminal means. Begin in the same spot, end in the same spot, different measurements. Comfortable with that? Awesome. Let me draw one more just because. Whee! There you go. Look at that guy. That guy, woo, that's a really big angle. Also, coterminal. So that's what coterminal angles are. And the unit circle. The unit circle is the circle whose radius is 1 unit and its center is at the origin 0, 0 of the coordinate plane. Points on the circle are related to periodic functions that we talked about last week. Those waves, so points along this circle create those wavy patterns from last week, create our periodic functions. So if this is the unit circle, then the 4 dots that are on the x and y axis, we know what their coordinates are. Because if it's the unit circle, then we know it has a radius of length 1. That would make this dot, which is exactly 1 to the right of the origin, 1, 0. This dot, which is 1 above the origin, we have coordinates 0, 1. Yeah, I'm not really sure what just happened at my door or why that had to happen. I am very happy, though, that it was captured on video, so hopefully we can hear this guy rapping on the friggin' door. Anyway, this coordinate is 1 to the left of the origin, so its coordinates are -1, 0. And this one is 1 below the origin, so it has coordinates 0, -1. Now, just so you know, this didn't have to be a radius of 1. It could have been any other circle of any other radius. If this had been a radius 2, this would have been 2, 0, 0, 2, negative 2, 0, and 0, negative 2. These, which fall in the x and y axis, are always radius away from the origin. Up, down, left, right. Pretty cool, right? Right. Great. A moment ago, I drew this. Whee! And you might have noticed that I had a blue and a red arrow that went opposite directions. Those mean something that hopefully you remember from geometry. One of them is a positive angle, and the other is a negative angle. Positive angles begin at the positive x-axis and go counterclockwise. Negative angles begin at the positive x-axis and go clockwise. So on this image, my blue angle is positive. My green angle is positive. My red angle is negative. Because if you go counterclockwise, that's the way you're supposed to go, your angle would be positive. If you go clockwise, that's actually the opposite way you're supposed to go, your angle is negative. This example says, sketch an angle. Notice I skipped over this word because I don't care. Sketch an angle whose terminal side is in quadrant 3. Maybe we should label our quadrants. This one is quadrant 1. This one is quadrant 2. Down here is quadrant 3. And lastly, bottom right is quadrant 4. Someone asked me last period, do you have to use the Roman numerals? No. Just know that they will almost always be presented to you as Roman numerals. It's not wrong to say quadrant 4 and put the number 4 next to it. I don't care. But College Board is always going to present it to you with the Roman numerals. Is everybody cool with 1, 2, 3, 4 in Roman numerals? Yes? You guys remember learning, excuse me, sorry, I just hit that puberty. You guys remember learning that the quadrants are numbered that way, 1, 2, 3, 4? You remember learning that in like 7th grade math? Did you ever wonder why they're numbered in that order?
Because left to right.
Because angles. Because trigonometry. That's why. 1, 2, 3, 4. That's why. That's why they're numbered like that. It says, sketch an angle whose terminal side is in quadrant 2. 3. I can read. 3. There it is. You don't need the other side that's on the positive x-axis, but I drew it anyway. It's hard to see, but there it is in orange. It says it's negative. How can I make this negative? Very simple. Just have it open clockwise. There. I just drew a negative angle whose terminal side is in quadrant 3. Ta-da! That's it. So far, so good? Awesome. By the way, if I were to have drawn a positive little roundy thing here, boop, that would have been coterminal. 1 positive, 1 negative. That's not what he told me to do, though. So. And because I'm a nerd and I figure I might as well give you nerd information, you guys, you've all seen clocks that have Roman numerals on them, right? Yes? Everybody seen those before? They look fancy, don't they? Okay, start looking around when you're out in public and you see Roman numeral clocks. Look for the number 4. You're going to see that it is usually not IV on the clocks. It usually looks like this, just with the 4th line on it. Yeah. The only reason why I think it's like that is because most people struggle with Roman numerals, and the Roman numeral 5 is V. The Roman numeral 6 is VI. So the numbers in order would go, and this is as you go around the clock this way, so it would go like IV, V, VI. So I think it would confuse people, so that's why they do that. So most of them won't say IV for 4. Most of them will just have 4 straight lines. Start looking. There's none in here. He instantly started looking. I don't have any in here. Oh, you looked them up on the internet? Yeah, I'm not joking. I remember one of my buddies told me that. I was like, no. And instantly looked because I have a clock in my house with Roman numerals on it. I was like, you got to be effing kidding me. You know, how many Roman numeral clocks have you seen in your life and you never realized that 4 was wrong? You know? They assume people are stupid? No, they know people are stupid. Yeah. The assumption is correct? Yeah. Alrighty. So, sine, cosine, and tangent. These are the three, let's call them primary trigonometric functions. Are there only three? No, there's actually 6 that we will talk about, but these are the 3 we'll begin with: sine, cosine, and tangent. And you should have been introduced to these 3 functions in geometry, and then hopefully reviewed once again in Algebra 2 Honors. And then show of hands, who in the room learned SOHCAHTOA in geometry? Almost all of you? Walter didn't raise a hand. Okay, so raise a hand if you didn't learn SOHCAHTOA in geometry. Doesn't translate very well to the video, but my hand is up. I did not learn SOHCAHTOA in geometry. My teacher was like, here's the functions and the fractions. Good luck. It was hard. It didn't go well. Yeah, no, it didn't go well at all. Yeah, and then when I found out that there was a word for it, I was in Algebra 2, and I was like, man, I really wish I had known SOHCAHTOA last year. Would have made life a lot easier. Speaking of SOHCAHTOA, let's go ahead and write it out. SOHCAHTOA. This is a shortcut for remembering which side lengths your trigonometric function uses and in what order. Sine of an angle is the opposite side divided by the hypotenuse. Cosine of an angle is the adjacent side divided by the hypotenuse, and tangent of an angle is the opposite side divided by the adjacent side, which is what you see here, here, and here. Now, I was saying of an angle. In this image, we have the symbol, the Greek letter, lowercase Greek letter, theta, T-H-E-T-A. This is what we usually use to represent an angle. And just like when I taught you logarithms, you have to get used to understanding that sine, cosine, and tangent are operations, just like log is an operation. You can't ask me what is the value of sine. And I go, I don't know. What is the value of square root bar? You see, it doesn't make any sense because it's an operator. It's an operation. It does something to a number. Its set of instructions are form a fraction, and depending on which function you're looking at tells you how to build the fraction. Sine of theta says, stand at an angle and make a ratio, the opposite length divided by the hypotenuse length. Cosine of an angle says, stand at this angle, make a ratio, the adjacent length divided by the hypotenuse. And tangent of an angle says, stand at an angle, make a ratio, the opposite length divided by the adjacent length. Okay? Okay. In geometry, when I was a geometry teacher, I learned that some people struggle with the words opposite and adjacent. Opposite means across from, boop, and adjacent means next to. Cool beans? Cool beans. Now, when we are doing our trigonometry, our thetas will always be at the origin. What we have here is some radius of a circle. Let me go ahead and put a dotted edge of this circle down, since you can see that it is, in fact, a circle. Here I have a radius of a circle and an altitude from this point on the circumference of the circle straight down to the x-axis. One more time, straight down to the x-axis. Never draw a line to the y-axis. Never, ever, ever do that. We always draw them to the x-axis. Great. Hey, look, a right triangle. And in this right triangle, I have a horizontal leg, which has a length of x. It's adjacent to my theta. I have a vertical leg. It has a length of y, because, well, that's the coordinate, x comma y. It's opposite my theta. And then I have a hypotenuse, which is the radius of a circle. Did you have a question for me? Yeah, you. No? Okay. You know what this allows us to do? If this length is x, and this length is y, and this length is r, it allows us the ability to use x, y, and r instead of adjacent, opposite, and hypotenuse. But Mr. M, I like SOHCAHTOA. I got bad news for you. It doesn't always work. You know what always works, though, is using x, y, and r. Let the coordinate x comma y be some point that is r units from the origin of the terminal side of a rotating like, whee, around this circle. If theta is the angle in standard position to the ray, then the following ratios will hold true. What we have here is this image zoomed out so that you can see the whole circle. There's the coordinate xy. Here's that altitude going to the x-axis. But Mr. M, you said never to the y-axis. Yeah, this is just to show you that this length and that length are the same, but the point is it's an x. So I'm going to throw that x right here. And this is y, and this is r. Instead of saying that sine of theta, bless you, is the opposite over the hypotenuse, we will say it is y over r. But Mr. Mine likes SOHCAHTOA. You're going to have to let it go, trust me. Instead of saying cosine is adjacent over hypotenuse, cosine of theta is adjacent over hypotenuse, you will say cosine of theta is x over r. R being the radius, the distance from the center to the edge. And lastly on here, instead of saying tangent of theta is opposite over adjacent, you will say it is y over x. Yes, London? If it's just the same thing, why bother? Because what if I told you were right here and this was your angle? What is sine of a straight line when there is no such thing as the opposite and the hypotenuse? There you go. Where the SOHCAHTOA fails, XYR won't. And that's why. Oh, hey, there's something very interesting written right here. That tangent of theta equals sine of theta divided by cosine of theta. This is called a trigonometric identity, a trig identity. This is your first trig identity. It's not the most important, but it's a good place to mention it. And you might be wondering how we know that's true. It can be demonstrated very, very simply. I'm going to take this, and I'm going to take this, I'm going to write them here, and I'm going to do some work on them. Sine of theta is y over r, and cosine of theta is x over r. Now, I know that most of you don't like fractions. You remember how we get rid of fractions? Multiply by the denominator. So what I'm going to do is I'm going to multiply both sides by r here and here, as well as over here. So in green, what I'm going to get, because these are just going to cancel and so are these, what I'm going to get is that y equals r sine theta. And over here, I'm going to get x equals r cosine theta. Therefore, if you were to build tangent of theta, which is y over x, you would get r sine theta divided by r cosine theta. Your r's would cancel off the top and bottom, and you're left with sine theta over cosine theta. Isn't that neato mosquito? A trig identity. Now, I'm aware that all of you really love SOHCAHTOA. So what I'm going to do is, for a little while, I'll use these letters, O, A, and H, before I write my X, Y, and R. Just so you can kind of get used to the transition between them. I've started using the terminology memory breadcrumbs in my Algebra 2 Honors class. Here's your memory breadcrumb on which one is which. In quadrant 1, in fact, I'll draw it as such. That way you can see I'm in quadrant 1. You've got a theta here. You've got an x here. You've got a y here. This is a radius for r. This side is adjacent to theta. This side is opposite from theta. And this side is your hypotenuse. This is your memory breadcrumb. This is how you're going to master x, y, and r, and how you're going to let go of SOHCAHTOA. We need to have mastered x, y, and r to be successful. Please believe me when I say that. A whole bunch of cameras coming out and taking pictures of me. I hope you got my good side. What? My good side or a picture? Oh, okay. Did you zoom in?
For you?
Did you zoom on the image on the board?
Yeah.
Oh, then you missed the face I was making at you when you were taking your picture. Ah, too late. It's gone now. It's forever gone. It's forever gone. No, I'm not doing it. No, you get a picture then. You can get a picture of his picture. No, pay attention. We're going to still learn here. Okay. The figure above shows a circle with radius r. How do we know that? That right there. You see how that coordinates at r comma 0? That means my circle's edge is r units away from the origin. That means these 4 triangles actually all have the same radius. Can we agree that the radius of a circle is always a positive number? Can we agree to that? Okay. So it doesn't matter where MATH, by the way, that spells math. It doesn't matter what quadrant you're in, your radius is always positive, right? Awesome. Great. The figure above shows a circle with radius r centered at the origin with an angle of measure theta in standard position. The terminal ray of the angle intersects the circle at point A, whose coordinates are unknown, so we will just say they are x, comma, y. The points M, T, and H are the results of simply reflecting coordinate A across the y-axis, which goes left, across the origin, which is a weird thing to say, but it means the opposite side of the circle, diameter. It's the same result as going over the y and then going over the x. Oh, and then also the x. So from A to M is reflect over y, from A to H is reflect over x, and from A to T is reflect over both axes, or you could say reflect through the origin. Completely up to you how you want to say it. Well, point M. To get from A to M, am I reflecting over the x or over the y? I'm reflecting over the y. So if you go over the y-axis, what changes, x or y? Both letters were said. If I go from here to here, did I change x or y? X changed. And since it's the exact same thing, it's a rectangle here, whatever distance A is from the y-axis, M is also, except for it's on the other side. So over there, M's coordinates would be negative x, comma, y. Now I'm going to go to H. From A to H, from here to here. To go from A to H, I have to reflect over the x-axis. What changes when I go from here to here, my x or my y? My y. That means my x coordinate stays the same. It's positive. But now y is a negative value. And it doesn't matter if you go from orange or from green. Either way, you're going to get the same value for t. I forgot to write for point H, x, comma, negative y. There we go. You guys said when you went from A to H that it changed the sign on the y value, right? Does that mean everybody's comfortable with me saying if I go from M to T, I just change the sign on my y value? There it is. Not too bad, right? You know what's interesting about this? You see this right triangle right here? And, this is a right triangle. With this coordinate, which would give me these side lengths, I can reflect that right triangle into any of the quadrants that I want. And that would allow me to do trigonometry in any of the quadrants that I want because it would just be that same x and y value, just maybe positive or negative or both, because you're in a different quadrant. So my x, y, r fractions could still be done. How neat. So I'll have to do a whole lot of this for these questions. Use the image from above to talk about this stuff. Let's find the sine of an angle whose terminal ray intersects the circle at point H. Point H is here. It's asking me to do sine of this angle. And it's always going to be sine of theta. Okay, it'll always be sine of theta. Theta could be from here, could be from here to here, could be from here to here to here. We're just going to say sine of theta. Cool? Theta means unknown angle. But what I do know is if I wanted to go to here, I'm using this length and this length as my adjacent and my opposite, my x and my y. Sine of theta is always And for this, we would have said SOHCAHTOA, so we would have had O over H. That's going to be our y value over our radius. Our y value in this picture is negative y. And for all of them, we said the radius was r. Wait a minute. That means if I'm in quadrant 4, where all y values are negative, sine of any angle that ends there is always going to be negative. Sine is negative in quadrant 4. I'll be lazy and write the number instead of the numeral. Part B says cosine at point B, point M. That's here. Okay, well, cosine of theta, let's see, cosine, we would have said adjacent over hypotenuse. That is the, memory breadcrumb, adjacent is, the x. So I have my x value over my radius. And if I go back to point M, I can see my x value is negative x. Radius is just radius. Negative x over r. Wait a minute. Radius is always positive. So if I have an angle that terminates in quadrant 2, where all my x's are negative, cosine will be negative. Very interesting. Part C says tangent of the angle whose terminal ray intersects at point T, that's here. So now I'm coming down here to quadrant 3. All right, tangent of theta. And we know that tangent, we've always read it as opposite over adjacent, but we got to get used to it. So memory breadcrumb, opposite is y over adjacent is x. So this is my y value over my x value. So if I go to point T, I can see my y value is negative y and my x value is negative x. Every coordinate in quadrant 3 is going to be a negative x and a negative y. So every time I set up a ratio in that quadrant, my negative signs will cancel and I will get positive y over x. That tells us that tangent is positive in quadrant 3. Again, I'll be lazy and use the number instead of the numeral. Have I done anything mind-boggling yet? Do you see how every little bit of knowledge kind of builds off of the previous little bit of knowledge? Trigonometry is going to be like that, where in order to go forwards, you're almost going to be forced to have mastered what we just did. We can't really slack on any of it. Here is the coordinate 4, 3, showing you that it's on the edge of a circle. That circle has a radius of 5. Isn't that neat? That if I drew this right triangle, its lengths would be all whole numbers, 3, 4, 5. That's known as a Pythagorean triple. 3 integers that form a right triangle. The numbers 3, 4, and 5 always form a right triangle. Because 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and 5 squared is 25. So, well, remember the biggest one has to be the hypotenuse, which would always be your radius. So yeah, 3, 4, 5 always makes a right triangle. It's forced. Pythagorean triples are kind of neat. There's a set number of them, and anything after the first set of them is like just multiples of others. For example, 3, 4, 5 times 2, 6, 8, 10. 3, 4, 5 times 3, 9, 12, 15. It always works because similar right triangles, if you can remember that concept from geometry. Anyway, other very famous Pythagorean triples that won't require you to use a calculator that you want to know. 5, 12, 13. If you haven't taken the SAT yet, 3, 4, 5 and 5, 12, 13 right triangles show up constantly on the SAT. It's big time important to know that. So 3, 4, 5, 5, 12, 13. And another very common Pythagorean triple that you'll see often is 8, 15, 17. Should sound familiar to you because I've already spoken to you about those three numbers today. I did it when the video was paused at the very, very beginning, but number 21 in the homework, 8, 15, 17. That's another Pythagorean triple. And there's others, obviously. Anyway, what do we have going on here? The figure at the right shows a circle with radius of 5, centered at the origin with an angle measured of theta in standard position. The terminal ray of the angle intersects the circle at point Q. Ah, see, look. Boop. Theta is actually out here. This angle right here is the angle that we reference when we talk about our SOHCAHTOA, our opposite, adjacent, or hypotenuse. Because of that, which I don't use SOHCAHTOA, but because of that, it's called a reference angle. I need you to understand that because it is just a reflection of this blue triangle, that the angle that's within the blue triangle and this reference angle over here are exactly the same measure. That's why we call it a reference angle. Anyway, I'm trying to do trigonometry in this triangle. My theta is not even in the triangle. That's fine. It doesn't matter. We still reference the x, the y, and the r associated with this triangle. And since it's just a reflection, we actually know the coordinates of point Q. Just like a to m, all that happens is x becomes negative. Point Q has coordinates -4, comma 3, and the radius is still a 5. So sine at this theta, let's see, sine, memory breadcrumb, sine uses opposite over hypotenuse. Oh, it's y over r, okay. Sine is y over r. That's going to be 3 over 5. Cosine, adjacent over hypotenuse, memory breadcrumb, x over r is going to be -4 over 5. And tangent, opposite over adjacent, memory breadcrumb, y over x. And you'll notice that I write my x, y, r every time I go to use them, every single time. If you would like to memorize your x, y, r ratios quickly, write them every time. Anyway, y over x gets me 3 over -4, which makes the whole fraction negative. If I didn't tell you this, and I just said, hey, tangent is -3/4, you actually wouldn't be able to tell me if we were in quadrant 2, where x is negative, or quadrant 4, where y is negative. You have to know which quadrant you're in to know which one of these was the negative number. Now, if I told you, by the way, sine was positive, but tangent was negative, you go, if sine was positive, that meant y had to be positive. So if this was negative, that means x is negative. Oh, negative x and positive y, I'm in quadrant 2. So it's just this little like scavenger hunt knowledge, trip. I like trig because it feels like a puzzle. Do you have questions for me about that stuff, though? No. None? All right, other than the guy rapping on the door, this is going to be kind of a boring video. Nobody's asking questions. Number 5, example number 5, is a multiple choice example. The figure above shows a circle centered at the origin with an angle of measure beta. Hey, look, a beta. Did I show the other Greek symbols that we often use for angles earlier? I did not. I forgot to write them up here. Where can I write them? Let me just scroll these bad boys. It doesn't really matter. Here we go. I'll squeeze it in this image. So we have a theta, but the other Greek letters that are commonly used for angles are alpha, beta, we know theta, and phi. These are the 4 most common Greek letters that are used for angles. Alpha, beta, theta, phi. Because the letters A, B, C, D are usually used for coordinate names. Alpha, that is an alpha, and that is a beta. Alpha, beta, Well, because the Greek alphabet doesn't go A, B, C, D. The Greek alphabet goes alpha, beta, gamma, delta. That's why. But anyway, alpha, beta, theta, phi. Okay? Phi or phi, depends on who you are. I like phi, to say phi. All right, where was I? Back here? That's right. All right. Angle beta, it's in standard position. Terminal ray is right there. Hits point P on my circle. There's the coordinates. And you know what? I know the radius of the circle. Radius of the circle is 4. How do I know? Because that point is exactly 4 from the origin. So the radius of this circle is 4. I don't know x, I don't know y. But what I do know is that I'm in quadrant 4. And in quadrant 4, x's are positive, y's are negative. The question says, what's true about the sine of beta? Well, let's see. Sine of beta. Well, we know sine is opposite over hypotenuse. Memory breadcrumb. Opposite hypotenuse, y over r. So that's the y value over the radius. Let's see. Our y value happens to be negative y. That looks stupid. Negative y over the radius. So I'm looking for the one that says sine of beta equals negative y over r. There it is. Because r is 4. Because from here to here is the radius. Ta-da! Notice you didn't even need to know that r was 4. It was the only one that had negative y on the top of the fraction. Oh, I lied. That one does too. Yeah, but it has x in it, yeah. And the only one that has y's and x's is tangent, not tangent. At least as far as you guys know. Because remember, there are more trig functions than sine, cosine, and tangent. Why? Stop, why? Those are just the 3 regular ones. You know all of these are fractions, right? What do we often work with when we talk about fractions? Not, I mean, other than decimals, but I mean, like, what's something that we often have to use when we're working with fractions? Reciprocals. Yeah, buddy. If you flip every one of those trig fractions over, you have a different trig function. Not opposite. You mean the reciprocal of sine. The reciprocal of sine is the function cosecant. The reciprocal of cosine is the function secant, and the reciprocal of tangent is the function cotangent. They're not that confusing. It's weird for the first time when you just hear the words instead of seeing the math with it, but we'll get to it, okay? But for now, we're not worried about that. This is the last example for today. It says, let alpha be an angle in standard position whose terminal ray coincides with the line y equals negative 2x, and it's going to happen in quadrant 2. Sketch the scenario. So what I'm going to do is I'm going to take the edge of my calculator, because that's nice and straight, and I'm going to draw the line y equals negative 2x. I'm going to do my best at least. Negative slope looks like this. Picture not drawn to scale. There we go. There is a rough estimate of the line y equals negative 2x. And what we've been told is that the ray of our angle coincides with that line. So we'll say there's the ray of our angle. Drop a vertical line and altitude to the x-axis, and oh look, we have a right triangle. Our theta is out here because it is in standard. Oh, it's alpha, isn't it? Sorry, it's not theta, it's alpha. There we go. What can you guys tell me about this side of this triangle? It's got a negative x value, doesn't it? I have a negative x value here. Now, let me ask you a question. Using this line, if I told you go to x equals negative 1, what would the y value be? Positive Positive 2. If I told you use x equals negative 2, what would your y value be? Positive 4. And one more time before I ask the question, if I said use x equals negative 3, what would your y value be? Positive 6. So can we all agree that our y value there is positive? Okay, so let's not talk about positive negative anymore. I said 1, you said 2. I said 2, you said 4. I said 3, you said 6. How long is this? Double what the x value is, but it's going to be positive. And since we're going to be talking about sine and cosine, you know I'm going to need to know the hypotenuse, aka the radius, right? Do you remember how to find the hypotenuse of a right triangle if you know the two legs? Pythagorean theorem. So the Pythagorean theorem is pretty famous, right? It's a squared plus b squared equals c squared. The only one of those that matters is c. But we don't say hypotenuse, do we? We're going to say radius. And instead of a and b, why don't we say x and y? By the way, x squared plus y squared equals r squared is the equation of a circle that is centered at the origin. You would have learned that in Geometry Honors a couple years ago. And oh, we know what values to use for x and y. Our x value is negative x. Our y value is 2x. Well, negative x times negative x is positive x squared. And if you square the 2 and square the x, you get 4x squared. Hey, look, they're like terms. 1x squared plus 4x squared is 5x squared. We're going to take the square root of both sides so we know what our radius length is. Remember, we don't need plus or minus because at this point in the game, all the radii of circles are positive. Yes? You cannot take the square root of 5, but you can take the square root of x squared. So we get our radius is x root 5. Isn't that special? Bless you. Let us now fill out sine, cosine, and tangent of alpha. Sine, what color have I been using for sine this whole time? Orange for sine. Sine uses y over r. For us, that's 2x over x root 5. The x's cancel. 2 divided by the square root of 5. No reason to rationalize that denominator. Cosine, I've been using green. Cosine of an angle is x over r. Our x value is negative x. Our radius is x root 5. The x's cancel off the top and bottom, leaving me a negative 1 over root 5. Once again, no reason to rationalize the denominator. And for tangent, I've been using purple, y over x. Our y value is 2x. Our x value is negative x. The x's cancel to get me 2 over negative 1, which is just negative 2. Do you have questions about anything that we saw on the back page? Because now would be an excellent time to ask those questions. No? Too easy? Bunch of nerds.